Last time we started section 2.1, symbols and terminology, and we had taken a look at just a few key concepts from set theory as we began our discussion. We talked about what sets are. Sets are just a collection of objects, and those objects are called elements. We talked about three different types of notation for sets. We talked about word descriptions. That was pretty straightforward. Set builder notation, which looks pretty abstract, and we will actually make it look even more so with some of the things that we're going to learn today. And then we have this listing method where we simply list out all the things that are in our set. And we talked about that one last one, which was the null set, which is a set that has nothing in it. So we're going to pick up today with a few examples of those ideas and go from there. So this first set of examples wants us to list the elements in each set, and it asks us to do it two different ways. First, it says, I'll kind of label them as A and B, use set notation. So set notation was that set builder stuff that we did right here. Okay? And then the other one says to use the listing method. So that's going to be making a list. So we're going to be doing two answers for each word description they give us. All right, so the first one says, the set of whole numbers greater than 8 and less than 18. So if you don't want to do them in the order that's listed, that's fine. But eventually we're going to have two different answers, and they both have curly braces because the listing method and set builder notation both use curly braces. Set builder notation is the one we're going to start with just because it's the order that the question's listed in. And it wants us to do, for set builder notation, it's always the same. You put the curly brace, you put the X, and you put the bar. And remember, that is read as X such that. And then we're going to describe what X is. Now, one way to do that is to literally write down all the words that are in the description to start with, and that's not necessarily wrong, but there might be other things that my math lab's asking you to do or to do it in a more concise way. So while I could write that down and we could be done, I'd like to show you some of those other options too that are maybe less directly correlated to what we've already seen. So this one actually says that the numbers need to be greater than 8, less than 18, and be whole numbers. There's three conditions here. Okay, so you can probably tell me one number in this set. What's one number in the way that it's been described? 9. Right? 9's in there because 9 is greater than 8 and it's less than 18. Okay, so we're going to have our list of numbers. That's the second thing we're going to do. But what we're going to do first is we're going to actually do the set builder notation where we describe it with inequalities. So since it says that that the value is greater than 8, that means like this, right? X is greater than 8. And down here where it says it's less than 18, it means X is less than 18. But I want both of those things to be true at the same time, right? And, that's what the word and that's showing up in there. Both of those things have to be true. And the most concise way to do that is to write what I call a triple inequality. So we start with the smallest number, which would be 8. And since X is greater than 8, that means that 8 is less than X. So we write it in that order. Start with the smallest. And then we know that the X is less than 18. Okay, so we're starting with the smallest. We're going up to the largest 18, and X is sandwiched in between. Please do notice the inequalities go the same direction. They're both less than inequalities. So even though the original statement started out that X has to be greater than 8, I have switched it around and written it so that they're in the same order. Okay? I also need to tell it that it's whole numbers. Yes? Yes, okay. That's set notation or set builder notation, yes. I also need to specify that these are whole numbers because that was the description, right? It didn't say I have fractions, right? 8.5 is not an option, the way that this is described, and I need to make sure that my notation indicates that as well. And so I need a statement that says X is a whole number. And we're going to come back to this problem and a few others later and look at another way to write this when we have a little bit more symbol terminology, really, is what it's going to be later in this section to be able to put with this and make it a little bit less wordy. But for right now, this is what we have. All right, and then we're going to do the listing method. So this says that I need values that are greater than 8 and less than 18. So you guys already told me 9 is in that list, and 9's the smallest one in that list, right? 8's not in the list, agreed? Okay, we have to be strictly greater than 8. So 9's the smallest one in my list. And then what will happen next? 10. And how far are we going to go? Up to 17. Good job. Whoops. Okay, is that good? Okay, so we've given the two answers that it asks for. Make sure that you're giving the answer that it asks for in the right blank that it asks for, that kind of stuff, because my math lab's in particular, and it's grading for that. All right, so on number 2, it actually almost looks like a listing method already, doesn't it? I mean, they've listed out a few of the things, and they've put that ... in there. Well, that's fine, but the listing method actually means we list out every element, all of them, okay? Which means that there's sometimes we can't even do a listing method, right? If you were running all the numbers, not all the whole numbers, we'd be stuck because there's no way to write out all of the fractions and decimals in between numbers, right? So we're going to do that same set builder notation that we did before and the same listing method. And I'm just going to do them in the other order this time because it doesn't really matter. This is very nice because it's already written out partially, 2, 4, 6. So what number would come next?
8.
It'll be 8, right? So we have to stick with whatever the pattern is that they've already established. They've established that this is skip counting, right? We're jumping or we're writing down even numbers, however you want to describe that. So 2, 4, 6, 8, 10. And we're going to fill in all the dots with all the evens, right? So 12, 14, 16, 18, 20, and 22. So that's my listing method for this one. And now my set builder notation, the one that I'm going to go back up to, is going to look very much like the first problem. First of all, they all look like this. Curly brace, X bar. Always going to be like that. And then what comes next has to be describing this set. So if you look at these numbers, you can actually describe them kind of like we did with the first one. It starts at 2 and it ends at 22, right? So because it's easier to see, we could actually use the 2 and the 22, but instead of using a less than, we can use less than or equal to. I mean, we could use a less than, but we couldn't then use 2. We'd have to use something else. But 2 is included, so I'll just say 2 is less than or equal to X is less than or equal to 22. I can't stop there, though, because that would include, like, 5. And 5.5, actually, right? The way that I've written it. So I need to clarify the kinds of numbers that I'm looking at. Well, X is a whole number. That gets rid of my 5.5 option. What else do I need to say on this one that I... Yeah, you got to say it's even. Oops. If you want to, you can just say and even here. Or you can say X is even, whatever. But it's got to include the whole number part, and it's got to include the even part. My math lab might let you just put that it's even, assuming that even numbers would only be whole numbers, because otherwise everything kind of has the ability to be divided evenly if you're going to use decimals. So even itself might be sufficient enough. You can just see. Now I want to mention this last one here, the 2 to 22, where we listed them all out. Be careful inside of my math lab, because sometimes they'll ask the question where they say to fill in the dots between, in which case they would only be asking you to fill in from 6 to 20, right? Or they might ask you to write the entire thing out. So I see students just mix those up all the time. You've got 5 attempts, so if you're like, I'm pretty sure I did it right, just go back and be careful about the directions and how they asked it. All right, did they just want you to put the ... part and that's all you're supposed to be writing down as your answer? Or did they want you to write down the whole thing? All right? Okay, we have one more example here. The word set was left out. We're going to describe this set by set builder notation using X as the variable. So again, set builder notation always starts out with the curly brace, the X, and the bar. And the reality is that on this one, it's very straightforward. It looks exactly like the word description. We say X is rational. There's no starting and ending spot like they were on the last ones. This problem is considerably easier to actually write down. Again, after we have a little bit more terminology and symbols, we're going to come back to this one and we're going to write it one other way too. Okay, you guys ready? All right, so what we're going to look at next is we're going to look at sets of numbers. So on your paper, you have a big old blank spot on the right-hand side, yeah? Yours is way bigger than mine. So err on the side of a little bit larger of a rectangle than you might think that you need, because I have a condensed space. And I tried playing with this slide as I was even recreating it and still trying. There's just no way good way to write it. So I'm going to be dealing with a smaller space to draw in. These are different types of numbers. And in fact, as you look at all of them, they probably are all things that you recall hearing about. I'm not going to put you on the spot and say, tell me what an irrational number is right now. That may not be, you've heard of it. These are not words that are foreign. You've seen these words before. So what we're going to look at next is we're going to look at how we make sense of all of these different types of numbers. And we're going to think about it as how you learned numbers in school, grade school, growing up. So what I want you to do first is to draw a big old giant box, as big as reasonably you can. And you're going to divide the box into two pieces. I'll talk about those two pieces later. It doesn't need to be necessarily divided evenly. This is not an indication of like how many things are in each side or anything. It just need it divided. And I need to draw more stuff in the side that I've left more space. So that's why one side's bigger for me. All right, this rectangle and the whole rectangle, is all the numbers there are for the ones we're going to be working with. In particular, the ones we're going to be working with are real numbers. So this entire rectangle here, the whole thing, are the real numbers. So let me throw out something that's not a real number, because we're not going to be working with it, just so you can know there are some things outside of this rectangle. In particular, what's outside of this rectangle are imaginary numbers, like the eyes. If you don't know what I'm talking about, it doesn't matter. But if you do know what eyes are, that's the stuff that I'm leaving out, okay? So inside of this rectangle, we're going to start on the bigger side with a small rectangular square. So you're just going to start with something small here, okay? And inside of that small little rectangle is you when you were 3 years old. Well, you're not really in it, but the types of numbers that you knew then were. So when you were 3 years old and somebody said, count to 100, how did you begin? 1, 2, 3. Okay, so notice some things you didn't say. You didn't say 0. You didn't say -7. You didn't say 3/4, right? That was not a part of your number worldview at that point. You started with the number 1. So inside of this square, rectangle, whatever, I just want you to write a few of those numbers, and you can just put the ... on the end. These numbers are the natural or counting numbers. And they have a symbol that represents them more concisely than writing out natural numbers. That symbol is a capital N with 2 lines on the left. Okay? So it's not just the letter N. So when you see this written out by you or me, I'm always going to write the 2 bars. If you see it in printed form, even perhaps in my math lab, instead of doing the double bars, they might bolden the left-hand side instead. But it's kind of hard when you're using a screen or even on paper to write it bold and to really get that full effect. That's why you see the double bars.
You said double bars on the left-hand side?
Yes, double bars on the left-hand side. Okay, these are the natural numbers. So right here in the middle, we have our natural numbers. But very quickly, after you learn the counting business and so forth, somebody's trying to do some simple math with you and they say, like Johnny has 3 gummy bears. When Joey takes Johnny's 3 gummy bears away, how many gummy bears does Johnny have left? And we need the number 0, right? We need the number 0 to represent things that happen when we don't have any of something. And so our worldview about numbers expands ever so slightly to include one more number, the number 0. And it makes perfectly reasonable sense that we would need it. So what we're going to do is we're going to draw a box around the box of N. That box is going to include all the numbers, 1, 2, 3, 4, but it's also going to include the number 0. So if you want to sort of write them out, we're going to start with 0 now. And those numbers are called the whole numbers. be real careful about this because the number 0 either is or it isn't, right? And people get confused between natural and whole numbers all the time, whether they include 0 or they don't include 0. The natural numbers are the ones you naturally start to count with, and they do not include 0, but the whole numbers do. Just like with the N, we're going to designate whole numbers with a W, and just like with that one as well, it will have a double line on the left. Those are our whole numbers. Okay, so far so good? And then there's some day and you're riding the bus home and some kid says, well, I know you know what 5 minus 3 is, but do you know what 3 minus 5 is? It might have happened to me, right? When you're little, because you know that smart like 5th grader that just learned about negative numbers thinks they're really smart and you're not. And you're like, well, no, I know what 3 minus 5 is. You can't take 5 away from 3. That's ridiculous, right? Until you overdraft your bank account, right? Until you borrow that money on that credit card, yeah? Those are negative numbers, and they're very much a part of our everyday existence. Maybe they shouldn't be, but they are. And so we need negatives, right? We need some negative numbers. So we expand our worldview again ever so slightly. That line I drew before is not very straight, is it? Let's just shift it over a little bit. And so now we have everything we had before, 0, 1, 2, 3, and so forth, but we have also the negatives of those. So when we're writing them down, you'll often see them written as 3 dots, and then you start with -3, -2, -1, 0, 1, 2, 3, and they continue on like that. And these are called the integers. So again, I'll write them up here. Now, patterns would tell you that the letter I'm going to use for integers would be an I, but it isn't, actually. I don't know if it's only because of the fact that we have another word irrational later on, and so the 2 I's causing confusion. I'm not sure if that's the only reason why, but we actually go to the Greek letter for integers, and it's actually a letter Z. So we're going to use the letter Z, and the double line is in the middle of the Z. That's where it occurs. So our integers are the number, are the letter Z with the double line. Okay, so again, the number 2 is both is all of the involved, right? It's a counting or a natural number. It's a whole number and it's an integer. It's all of these things in one. Okay? The last box is the box that it's already in. We still have to talk about the right-hand side box, but the last box that is the box that it's already in, it includes all of your rational numbers. So these are rational numbers on the outside. Rational numbers include all of your decimals and fractions and things like that. So I can't list them all because that doesn't make sense, but I can give you a few examples, right? Like you could have the number 1/2. That's a rational number. Notice all the numbers that I've already written, -3 and 0 and 4, all those are all rational numbers too. But this gives us more. I get the addition of all of, the inclusion of all of my fractions. I get decimals, like 4.7. I even get repeating decimals, things like 0.3. The reason I get repeating decimals is because repeating decimals have a fractional form. In particular, anything that has a fractional form of integers gets included. Those are our rational numbers. Rational numbers are not R. Real numbers actually are. So the real numbers are given the letter R. Okay? So jot that down. Real numbers are R. The rational numbers are actually the letter Q, and it's not Greek for the reasoning why. The reason it's a Q with that extra line, throwing in there on the left, is because Q is for quotient. Quotient means division. That's what fractions are. They're the division or the ratio of 2 numbers. So we get the letter Q from the word quotient. Okay. Any thoughts as to what I have not included so far? Can you give me a number that's not here besides I, because I already talked about it, that doesn't have a home yet? Pi. Pi's over here. It's not the only thing over here, but it's definitely over here. Over here are our irrational numbers. Irrational numbers do not have a very nice, concise letter form. I don't know why exactly. They just should be I. That would be nice, but they're not. Your book uses this form where it does the real numbers and it removes, that's what that minus means, removes the irrationals. You take all the real numbers and you just remove the rationals, then you have the irrationals left over. This is one of those places where English words for irrational and rational do not correlate to what's going on, right? It doesn't mean rational makes sense, irrational's crazy. That's not what's happening here. But irrational means it doesn't have the form of being able to be written in a ratio, right? Irrational. Rational is ratio. So pi is one of those numbers. You might also remember, you may or may not, the number e. It usually comes in an Algebra 2 kind of course in high school. With interest, compound interest is where you see it come in. If you don't know it, that's fine. We're not going to spend a lot of time there. But e. A few others that you've seen and you might not think about are things like radicals where you can't take the radical form nicely, right? Square root of 4 is great. It's over here on the rational side. Square root of 2, not so much. If you were to try to put the square root of 2 in your calculator, it's going to spit out an ugly decimal that doesn't ever repeat, doesn't ever end, that kind of stuff. That makes it irrational. I cannot have it written in a ratio form. So there's lots of things that are over here on the irrational side, okay? We need one more piece of information before we can go backwards. So we're going to keep moving forward for now, but we need these symbols in order to be able to write the things we've done before more concisely. So we will come back to these symbols. Cardinality. Cardinality has to do with how many things are in a set, how many objects, right? So we talked about, books on my bookshelf being a set. Well, how many of them are on your bookshelf, right? How many, songs are in that playlist in your phone, or how many people are in our classroom? So cardinality is simply the number of items that are in a set. The symbol for it being written that way has an N in front of it, N for number, and then inside of the parentheses is the set's name. So maybe it's just like the letter A, like the number of items in set A. Or we could do like the number of items, and we'll do our class in math 1033B. So let's see, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 19, 20. We have 20 people here today. So this is 20. We may have people absent, I don't know. But N is 20. So the notation says the number of items inside of the set math 1033B, and it equals 20. So as we're taking a look at them, examples 4 and 5 want us to do just that. They want us to find N of A. Well, on number 4, they list them all out. That's very convenient. How many items are in set A? There are 7. Right? There's 7 items there. Okay, so if you make a mistake inside of my math lab, you should be able to be like, oh, wait, go back, recount. It's okay. You make mistakes counting all the time. Okay, it's not a big deal. But it's the number of items in that set. Now, on the next example, example 5 down here, they do not list them all out, right? So we need to make sure we're a little bit more careful here because I'm not just counting the numbers that are written. So if you need to write them out to see them, do that. Or if you just want to count them up, that's fine too. The thing you need to be careful of is it's not all the numbers, right? They're skip counting. They're skip counting by 5s. Right? So 5, 10, 15, 20. Count them up. How many of them are there until you get to 50? There are 10. Yes, there are. So the number of items in this set is 10. So far, so good? Okay. The most common problem students have with this is that they forget the notation means something, right? They want those parentheses like to mean multiplying or something like that. They don't. The parentheses are just setting something aside, kind of like parentheses are in written literature, right? Where they describe something, next to it. It's like that. It's describing what you're taking the number of. All right, there are 2 types of sets in general, finite and infinite. Finite means the cardinal number is a particular whole number. Remember, cardinal number just means how many of them there are. So if you can count them up, right, like this, like we did on the last 2, then it's finite. Make sense? I wrote down a 7, I wrote down a 10, those are finite sets. But if you have something for which you do not have the ability to count all the objects, that would be infinite. It just keeps going. So there's a couple of examples down here, 6 and 7, that want us to decide if the set is finite or infinite. So what do you think about number 6? It's finite. If I asked you to, you could tell me how many there are, right? It's a lot like number 5 where we did that. We have those dots, they're skip counting, all of that. But there's a specific number of things that I would count up. How about number 7?
Infinite.
It is infinite. What is it about this one that makes it infinite?
It doesn't have an ending point.
Yeah, yeah. It's this word greater, which means it doesn't have an ending point, right? Greater than 50. Well, I mean, you've probably ever, what I remember doing with my son when he was little is you'd say something like, when you go to bed at night, I would say to him, I was like, you know, I love you, you know, times 2. There's this book that says, how much do I love you? I don't know if you've read it before. And it keeps multiplying. Well, I'm going to multiply it by 2. Well, I love you twice that much. Well, I love you 3 times that much. Right? It just keeps getting bigger, but there's no way to end that discussion because the numbers continue going on forever. So this would be considered an infinite set. Right? That greater than number is the problem. Now, in particular, if this said less than, the way that it's working out, right, written, it'd be okay, and it would be finite, right? If you wanted, it says natural numbers, if you wanted natural numbers less than 50, we'd be good to go. Because the natural numbers start at 1. So you'd start at 1 and you'd end at 49, right? That would be finite. But if you said less than 50 and it was integers, it wouldn't work, right? So it depends on the words greater than or less than, but it's also depending on the fact that natural numbers have a starting spot, whereas like integers don't. Integers go infinitely in both directions, right? So don't just look at it and say, oh, she said greater than, so therefore, just be careful of the language used with what kind of set you're working with. All right, there is a new symbol that we are going to need, and you're going to see it be used a lot. It looks kind of like a capital E, but it's curved on the edge. It's not boxy at all. Okay? It's a Greek letter, actually. All right? It's a Greek letter epsilon. And so when we're seeing this written, this E kind of harkens to the word element. Right? It means is an element of. Now, we talked about elements last time. So if we're talking about the set of Math 1033B, you guys, each one of you are an element of that set. So I could say Imani is an element of Math 1033B. Okay? But I could use anybody else on campus. So I have a grader. Her name, I'll use one from last semester. His name is Parker. Parker's not in this class. Okay? So if I talked about Parker, Parker would be not an element of Math 1033B because he's not in our class. So if you want not an element, just like if you want not equals, you just put a slash through something. Right? That's the key mathematical thing to make not something is you just slash it. Okay? So we're going to go back now to a couple problems we did before using this symbol, element, and using these symbols for whole and natural and so forth. And we're going to rewrite a couple of things to see how else that you might either be asked to write it in my math lab, or if they're doing a multiple choice, be able to interpret what's being said, right? Which one is the one that I'm supposed to be picking? Which one is right? So we're going to flip back to the examples from last time, and we're just going to do this one right here, number 1, first. We'll just start there. So the phrase that we're going to be replacing is this one at the end that says x is a whole number. Okay? X is a whole number. And we're going to be replacing it using those symbols that we've just learned. So I'm going to erase all of that says x is a whole number. And instead, we're going to write it in symbols. So this is x. Okay, that's the same. And then we can use that curl E, right, that looks almost like a C with a line through it. X is an element of. And then I use the W with the bar on the left. This says x is an element of, or it is one of those whole numbers. And you can see how much tighter and more concise you can write it. Yes, ma'am.
On my math lab, is it going to ask us to write it in both of those different ways, or will it let us pick one?
It'll just depend on the problem. It does different things at different points. And sometimes even if it'll give you a question, it'll give you multiple choice options. And it might be that all the multiple choice options are written with the symbols or that all of them are written in words and you just pick. So that's why I want to make sure that you know the different ways of having it written. Yeah. We can do the same thing on number 2, right? Number 2 had some of those symbols going on. Right in this spot where it says x is a whole number, I can take that out. And I can write that same symbol in. X is an element of the whole numbers. And then actually I'll just delete this. And then I'm just going to write x is even. You could say and x is even, but anyway. We're going to do one more, which is number 3. This one said x is rational. That's the only thing it said, in fact. So in rewriting this one, I can do x such that x is an element of the rational numbers, like so. All right, I think we have just a couple things left to look at and we'll be finished. The example that we're going to do right here has to do with filling in the blank to decide if something is or is not an element of what comes next. There's one tricky thing that happens here, which is why I put this specific example in. On number 8, which says 7, it has a 7 on the left, and it has a set with some stuff in it on the right. And what you're trying to decide is if the 7 is an element of the things that are written on the right. Is it one of them? And the answer is yes, which means that in the blank goes the element symbol. 7 is, in fact, an element of the set that follows. But number 9 is actually tricky. What is it about number 9 that looks different than number 8? Those curly brackets. And those curly brackets change things. Okay, so if those curly brackets are present, what you have is a set. Okay, the 7 all by himself, he was an element. But that 3 inside of the curly braces, that whole thing is a set. Okay, this is a set. And a set is not an element. I don't care if there's a 3 on the right-hand side or not. It doesn't matter. Because the symbol I'm supposed to be putting in between is either element or not an element. And it's not an element because it's simply not an element. It's not an element of anything, right? So what goes in this blank is this symbol, not an element. Now, it can fail also by simply not being among the items, right? So we could have this 5 like this and so forth. This would also fail to be an element, right? Not because it's a set like this, but because this 5 is not one of those numbers. Agreed? So they can fail to be an element in 2 different ways. 1, because they're not listed in the stuff that comes next. Or 2, because they're actually giving you a set with curly braces to start with instead of an element to start with. Now, if you are given a couple of different sets, it is possible that sets are equal. So a set A is equal to B if every element of set A is in B and every element of B is in A. So let me give you a concrete example. If I were to talk about, and I did last time, right, my children, got 8 kids, and you were to talk about Dr. Hans's children. And if my husband, his name's Jeff and he's a pastor, so we're going to call him Pastor Jeff, were to talk about Pastor Jeff's children, those would be the exact same group of children, right? All of our children are both of our children. It's shared, it's not property, but it's shared people, right? Those are our children. Now, that's not true for every family. Sometimes there's a yours, mine, and ours mix and things going on. That's not our family's story. So those 2 sets are equal. However, if I were to talk about the people who are biologically related to me, right, like my extended family and so forth, and my husband were to talk about the people who are biologically in his extended family related to him, those would not be the same groups of people, right? Those sets would not be equal. So equal sets has to do with items being exactly matching up in one description and another one. So our last example actually wants us to write true and false. So you need to be a little careful with true false because when you're doing homework questions on true false, you might be giving the right answer and for the wrong reason because it's just true false, right? Or you might be giving the wrong answer and then, you just change it because now my math lab told you, well, you're wrong. You were like, okay, well, I wrote down true, so now it must be false, but I don't know why. So you got credit for it, but you don't really understand why it's that way. So be very careful that you understand what's going on and why. So on the first one, number 10, it's asking us to write whether or not this statement is true. This says that 6 is an element of negative 2, 5, 8, and 9. Is that true or is that false?
False.
That is false. So we would write down that it is false. It's not false because it's a set. It's false simply because it's not in that list, right? It's just not an element of it. The last example, number 11, actually is a set equality, or at least it's asking you if it is. So you've got curly braces things on the left, and you've got curly brace things on the right. These are two sets, and they're telling you in the problem that they're equal, and you need to verify if they aren't, right? If they are or if they aren't. Now on the right-hand side, it's very clear. I know exactly what's in this set because it's written in listing method. It's the numbers 1 and 2. So the question I have to decide is if the things on the right are exactly 1 and 2. If they are, then I'm good. If they're not, then I'm not. So on the right-hand side, it says a natural number less than 3. So which ones are my natural numbers? 1, 2, 3, 4. Those are natural numbers. So which of those natural numbers are less than 3? 1 and 2. It's exactly what it is on the right, yeah? So this statement would be true. All right.